Good afternoon, everybody, and nice to meet you today. My name is Mohammad A Wahab. So, let me talk about the title of this work. Microstructure and properties of polyimide and polysesquioxane have been complete. 1. Let me talk about the introduction of this work. As you know, well, organic and hybrid composites have become increasingly important because of exceptional thermal properties, mechanical and electrical properties, which have been widely used in aerospace, mechanical, electronics and microelectronics system as well. As you know, well, the hybrid composite system concept comes from the dissimilar methods to acid the properties that cannot be acid by individual components. In this work, the objective in forming the organic hybrid composite with improved properties has been developed in the last few years from the dissimilar composites to acid with good properties and that cannot be acid by individual properties. And in this work, we report that polysesquioxane is not only important in low dielectric materials, but it can also provide the thermal properties, mechanical properties, and as well as it contains the structure of the molecules. And these hybrid composite materials can be mostly produced by Chazelle method of 2 stages. First stage hydrolysis of metal oxides, and second one consists of a condensation reaction as below in scheme. Let me talk about the scheme 1 is a typical solvent reaction. As you are seeing here, first one reaction is hydrolysis of metal oxide, then is produced cyanol, and second one is alcohol condensation, and third one is water condensation. And after that, it will produce a network structure through by this reaction. As you know well, for this solvent reaction, we need this component: water, solvent, acid medium or basic medium. Whereas the M is the represented by network forming elements such as zirconia, silicon, titanium, zirconia, any other materials, and R is the alkaline group with this formula. And in this work, we made polysesquioxane polyimide hybrid composite from BPDA, ODA, polyimic acid, and TBS, that is polysesquioxane, by solvent process. In this paper, we wish to report that the influence of TBS on the structure, microstructure and interfacial interaction and thermal stability. Let me talk about the figure 1, which indicates the prepared condition of polyimic acid and hybrid solution and hybrid composite film. First we dissolve ODA. What is ODA? ODA is oxide. First dissolved in DMASA, then it was stirred for several hours, then after getting complete solution, then we add here BPDA, and then we stirred again for several hours to mix a homogeneous solution. Then we got this PAA solution, then we add here polysesquioxane water with different amounts as per our need. Then this is the hybrid solution, then we add, dried at different imidization temperature, and then hybrid film. And then characterization and properties. That was the figure 1. Let me talk about the chemical structure of our investigation. That is the 4,4-oxidiniline and BPDA. That is 3,3,4,4 biphenyl dianhydride. And we mix it equimolar ratio to get the high molecular weight polyamic solution. And then dried at different temperature, and we got this polyimide from BPDA and ODA. And this one the polysesquioxane structure B, TBS, trihydroxyvinyl silane. And this all chemicals used in our investigation. Let me talk about the figure 1. Figure 1 indicates the preferred condition of polyimic acid and polyimide silica hybrid materials. As you are seeing here, some first column is indicate the simple code. Second one, PA solution. Third one, TVS, that is polysilsesquioxane. Add area as per weight percent. And silica, this we calculated from here. We assume that the silica solidization was completed. And these are the film state. And let me give the abbreviation. T is the light yellow transparent, O is opaque, and already I described this one. Let me talk about the figure 3, which is indicated the iris spectrum of polyimide and hybrid composite. I would like to talk first polyimide. This one the polyimide, the black one. The polyimide, as you are seeing here, there are some several characteristics. This one, 1780, 1711, 1721, 171368, and 1171, 1830, and 730. All are fixed come from the polyimide. And as you are seeing here, that is the characteristics fixed, and this one. And which indicate the 5-cyclic member of polyimide ring. And as you are seeing here, another one peak, this one, 1368, this comes from the CNC axial bond. And this bond comes from the polyimide deformation ring. And as you are seeing here, here is the one, another one, characteristic which didn't appear here, that is 1650. That is the carboxylic peak. It didn't appear. So, if you inspection of this figure, then you can understand here that there is no peak for carboxylic acid. It is meaning that the conversion from polyimic acid to polyimide is successfully converted. And then, as you are seeing another several curve here, that we increase this polysilsesquioxane amount. Then, and after adding polysilsesquioxane, and we can find several new peak. That peak, this peak is vinyl group. That is, this comes from our polysilsesquioxane. And 1621 this peak. Another one peak. This peak 1421 peak. And this one the characteristic peak from vinyl group. And as you are seeing another one broad peak here. This peak comes from the SiO-Si bond. Another one, new peak. As you are seeing here, this peak, these are not peak here, and this peak, we are assuming that this was the new possible associated peak with cross-linking peak here, and this peak 8840, this can be C6H4 or SiO-Si bond. As you are seeing here, this peak comes from incomplete hydrolysis of TVS. This is support the incomplete hydrolysis. This phenomenon arises because of TVS low functionality. That is, this three functional group is here. Another one, steric hindrance, come from the vinyl group. And another one, you can see here that after adding polysilsesquioxane, the peak intensity is increased, and so we can conclude from this figure that the interaction between the polyimide and polysilsesquioxane. That was the figure 3. Now I am going to talk about the polysilsesquioxane structure. Figure 4 indicates the structure of polysilsesquioxane. Where is the V is the group. After hydrolysis, it becomes like this structure. Let me talk about the figure 5, which indicates the XRD patterns of polyimide and hybrid composites. First, intensity as a function of angle. As you are seeing here, first polyimide, this one. Polyimide figure you are seeing here 004. This is not. This is 004, 100, and 200, 210 peaks. And polyimide peaks normally 110. As you are seeing here, this is two sharp peaks considered as a amorphous halos, and other peaks come from the molecular chain and packing of polymers from PPD or ODA. And this friction normally comes from the repeating unit distance of BPD or ODA. And after adding silsesquioxane, as you are seeing here, increasing amount, the peak is shifted to the low side. And it is meaning that the interporosity of this polyimide is changes with increasing this increasing amount of silsesquioxane. Another one you can see here, the intensity of this polyimide is decreased after adding silsesquioxane. It is meaning that some interaction is here and some interaction is here. That was the structural information of polyimide and hybrid composite. Let me talk about the thermal stability of hybrid composite and polyimide. As you are seeing here, this is the polyimide, and after adding silsesquioxane, the first decrease it comes from the two phenomena. First, the incomplete hydrolysis of TVS. This is in the our FTIR, and another one, the low concentration silica condition that cannot improve the thermal stability of polyimide. As you are seeing here, up to 20% it develop the polyimide thermal stability, and after when it is arrived in 30%, then it decreases again, become a vinyl group. Let me talk about the micrographs of TVS, silsesquioxane, and this one theos. We reproduce this data from our published result from our group, and this is the same polymer matrix with this one the silsesquioxane and then this one the theos. As you are seeing in the white particles, white particle indicate the silsesquioxane. Here is the silica metal theos, and then as you are seeing here, this particle size is the particle size around 0.15 to 0.25. It is meaning that the microcomposite nanocomposite formation, and these are also there, and then here is the particle size around 0.5 micrometer. It is meaning that it is also microcomposite and nanocomposite formation information from this two figure. Then considering this two figure, if we want to compare this figure, then we can see here that particle size is this, smaller than this one. Let me talk about the AFM image. We produce here three images. This was the silsesquioxane 20%, this was 30%, and we reproduce this data as I told you before for comparison and to get the information about the interfacial interaction and what is the difference between the TVS and theos. As you are saying, we can make one common explanation for this three figure. As you are seeing here, the black surrounding is corresponding to the silica materials, and continuous phase for the organic polymer phase. And as you are seeing here, there is a 20% silsesquioxane, this one 30% silsesquioxane. And as you are seeing here, 20% silsesquioxane, there is a hole. This hole can be comes from some anhydrolysis. Silsesquioxane can be pulling out, or there is another one possible reaction between the carboxylic group of silsesquioxane and phenyl group of TVS, which can produce the saline ester. It can be removed. That is the pull out during the humidization temperature. That's why there is the hole. So as you are seeing here, compared to this one, as you are seeing interfacial interaction between this and this one, good interfacial action with the higher silsesquioxane amount. And compared to this one, as you are seeing here also, this between 30% silsesquioxane and this one 30% theos silsesquioxane. Compared to this one, we can see here the interfacial interaction of silsesquioxane is higher than this one. And let me give brief idea about the particle size. This one particle size is 0.84 micrometer, and this one 0.25 micrometer in the small size, and larger one is 0.8 micrometer. and this one 1.5 micrometer in larger size, and a small one is 600 nanometer. So compared to this one, and this small particle size is acid by polysesquioxane, and compared to chaos. And another one, roughness is increasing order. This one is 6.11, this one nanometer, this one 36, this one 60 nanometer. So if we increasing order, if we see there, between this one, we can find here that polysesquioxane is smaller particle size compared to this one. So let me conclude my work. So new polyimide polysesquioxane hybrid composite from polyimide and polysesquioxane being made here, and here confirm the silsesquioxane bond, that is the SiO-Si bond, as well as the conversion from PAA into polyimide, and interaction between polyimide and polysesquioxane domain. And amorphous region of this imide phase is increased after adding polysesquioxane, and as we have seen there, the periodicity also interrupted after adding polysesquioxane, and thermal stability also we have seen there found to increase by adding polysesquioxane, even though they show low thermal stability than polyimide. And as we have seen in our micrographs and AFM, the size of polysesquioxane domain is first in BBT/ODA polyimide matrix decreased when compared to that of silica in the same PI. And we also have seen the overall FTIR, XRD and AFM result if we compare to the interaction between polyimide and vinyl group modified inorganic domains supported by our FTIR, XRD and AFM result. Thank you very much for your kind attention.